All right. So I have your exam 3 actually graded, and I put your grades online already. If you have taken the exam, that's one student still is in quarantine. She will take the exam later, so I won't be giving back your exams as of now. But you can check your exams 3 grade and your current grade for the class. Okay, as I put that in the feedback of your exams 3, so that gives you an idea what you stand as your grade in the class right now. Okay, um, so there are two more homeworks. They're online. So number 10 will be due next Tuesday, and then number 11 will be due on the Monday, um, and during the finals week. Okay, so only two more homeworks, and then final exam will cover those two homework assignments problems similar to them. Okay, final exam will be on Wednesday on the 21st. It's a different time than the class time, so 7:50 um, to 9:40. Okay, and then we'll be meeting in faculty 108 for the final exam. Okay. Um, so today we'll be starting to look at optics, pretty much focusing on geometric optics first, and then later next week at some point we'll be looking at wave optics. Okay, so I think we can finish the um, chapters on optics in probably in 3 lectures. Okay, so we'll be done with class on Wednesday. That's my goal. So then on Friday and Monday after next week, you can have extra time to prepare for the final. Okay. All right. So let's get started on chapter 25 on geometric optics. So first, before we start it, let me give you out this property of the light. So when light propagate in medium, we actually use like arrows, a line and arrow to represent it. We call it ray. So if light moves in a uniform medium, then it actually travel in a straight line. Okay, and it will change direction if it interact with material. So for example, if it hits the material, get reflected, or enters the material, then the directions will be changed. Okay, and for most of the um, things you need to use here in geometry optics is about geometry and simple trigonometry. Okay, so those two um, areas of knowledge will be used on geometric optics. Okay, so first let's take a look on when light hit the surface and get reflected. We have learned this in lab. So if you have a instant light, we call instant ray, hits the surface and will get reflected. So the angle the instant ray makes with the normal direction of the surface would be equal to the angle the reflected ray made with the normal direction. So that's called law of reflection. So you have theta I, the angle of instance equal to the angle of reflected. Okay. Now, if you have a very smooth surface, then the same um, rays coming in contact with the surface with the same instance angles. That means the parallel rays comes in, hits the surface, it will get reflected at the same angle with respect to the normal direction. Okay. Otherwise, if you have a rough surface, so parallel rays hits the surface because each ray will hit at different locations. So because this is a rough surface, so the normal direction at each location will be different. Therefore, reflected rays will be scattered in random directions. Okay, they are not parallel as the smooth surface would do. Um, so if you have a smooth surface, so then the reflection will be, we call it specular refraction. For a rough surface, the refraction is called diffuse refraction. Okay, so you might be thinking that diffuse refraction is not good, but it's actually pretty useful when you are driving in dark. So then the headlight of your car will hit on the road surface. Some of the reflecting will come back to your eyes, so you can see what's the condition of the road. Okay. If it's pretty smooth surface, then you will not be able to see what's the condition of the road, because the ray reflected off in the opposite direction will not come back to your eyes. Okay. So it's not always a bad thing. Okay, let's take a look on one example associated with law of reflection. So it says you stand 1.5 meters in front of a wall and gaze downward at a small vertical mirror mounted on it. Okay. In this mirror, you can see the reflection of your shoes. If your eyes are 1.85 meters above your feet, through what angle should the mirror be tilted for you to see your eyes reflect in the mirror? Okay, so it says the location of the mirror remains the same, only its angle to the vertical is changed. All right, so let's take a look on this one. So for geometry optics, you want to sketch your problems and then see what's the geometry involved. Okay, so we'll be doing that to get started. All right, so you can say this is a vertical wall where you have a mirror, a small mirror, a very small piece of mirror here mounted vertically. And you are standing 1.5 meters away. And you can see your shoes. So let's say your shoes are somewhere here. And you are standing over there. Okay, so the fact that you can see the shoes, so your eyes are somewhere here. It says from your eyes to the shoes are that distance is 1.85 meters. Okay. So the fact that you can see the shoes is because the light comes up the shoes will hit this mirror, and then it get reflected, and that light will hit your eyes, so then you see that. Okay. So you have a mirror here, you have reflection here, so that tells you that this angle theta I would be equal to this angle theta R. Okay, according to the law of reflection, so theta instance is equal to theta R reflected. Okay, so it's asking you, so in this case, because this mirror is pretty small, if you have larger mirror, you will be able to see your eyes in the mirror, but this is very small. So then you can imagine the light comes off your eye, will hit the mirror, and then will get reflected in this direction, right? So this is where it will go. Just go there and then hit there and then get reflected. So in order to see your eye, you need to put something here to receive the light comes off from your eye, get reflected. Okay, so you'll not be able to see your eye in this geometry. In order to do that, you will tilt the mirror, so that the light comes off your eye, will hit the mirror, okay, and then get reflected right back. Okay, so that's what would have to need to be happen there. So you'll tweak your mirror in that direction. So then the normal direction is the same direction as the ray comes off your eye hits the mirror. Okay. So then that's your new normal direction. So your normal direction moved from here horizontal to that. Okay, so that means that's the angle you want to find out. Okay, so that means you're looking for this angle theta of reflected. Okay, so that's what you are looking for. All right. given that this is 1.5, this is 1.85. Now my figure is not quite scale, but you can see that this is should be the horizontal direction because the mirror was originally vertically mounted, so its normal direction should be horizontal direction. Okay, then that should hit this at the right angle there. If this angle is the same as this angle, then this distance from the eye to where the normal direction of the mirror will be equal to this. Okay, so that will be divided, the height from the eye to the shoe will be divided by into two halves. Okay, one half here, one half there. Okay, so you can see then this is one half or 1.85 meters, and then this is the 1.5 that should be parallel to that. So you have this guy, you should be able to figure out this angle, okay, from the geometry. So tangent of theta r, tangent of this guy should be this side divided by that side, okay? Should be the 1/2 1.85 meters over the 1.5 meters, okay? Then you can solve your theta r. Theta r will be tangent inverse of the 1/2 times 1.85 meters over 1.5 meters, okay? And that will give you 31.66 in degrees, okay? That's how much you want to tweak the mirror so that you can see your eye in the mirror, okay? All right. Any questions you guys might have? All right. So if not, let's move on here. So let's take a look on the image formed by a mirror. In this case, we'll refer to plane mirror. So it's a flat mirror, okay? So when you get up in the morning, you probably have looked into the mirror. And so then you'll see your image in the mirror, okay? So for the, this can be, we can use the ray diagram, so which means you can locate like 2 points from one object. So in this case, your body, you can take a point over there. You can draw this. So light a ray comes out from here, will hit the mirror and then get reflected into your eye. And now the image appears to be behind the mirror, okay? Because this ray hits here, it can back extend. It appears like to be here, coming from here. You can also pick a point from your foot here and then hits the mirror, gets reflected. So then its image again is behind the mirror. And the angle should be the same. Theta I, theta r should be the same. Similarly for that, okay? So from the geometry, you can actually determine that for the image behind the mirror, okay, it's behind the mirror and then it should be the same size as the object. Okay, so if this is object, then it should be the same size. All right, and then it should be the same distance, appears to be in the same distance. If you are, say, if you are 1 meters away from mirror, then your image should be 1 meters away from the mirror as well. It's behind the mirror. Okay. And when you look into the mirror, you'll feel like if you raise your right hand, then your image will raise its left hand, right? So that's what the mirror image will give you. So then the properties of mirror images are those three. So the mirror image is upright, but appears reversed right to left. And the image appears to be the same distance behind the mirror that the object is in front of mirror. The image is the same size as the object, okay? So let's take a look on one example on this for the image of prime mirror. So this one says you hold a small mirror, plane mirror somewhere here. So this is the plane mirror This is 0.5 meters in front of you. So the distance, this is the distance, okay? All right. And it says the mirror is 0.32 meters high. So this mirror is 0.32 meters high. And in the mirror, you see the image of a tall building behind you. If the building is 95, so 95 meters away from you, what vertical height of the building edge can be seen in the mirror at any one time? Okay, so that's asking how much you can see from the building of the building. All right, so from the figure you can see to see the what range of the building would be. You'll see an image of the building right in the mirror. So we can draw that. Let me just draw that. So I'm going to just draw the mirror. So this is the mirror. Point 32 meters in height. And then this is the building behind you. This is where your eye is. Okay. It says the mirror is 0.5 meters from your eye. And then this is 95 meters. Okay. Now you'll see this is the wall of the building. You'll see an image of building somewhere behind the mirror. So this is 95. So that means from the building to the mirror, this should be 95.5 meters. Okay. 95.5 meters. So the image of the building should be also 95.5 meters behind the mirror. Okay, so the same 95.5 meters. That's where the image of the building will be. Okay. So this mirror is small. That means it has a top and bottom edge. Okay. So in order to see what would be the range of the building that you can see. So then from the top of the mirror, there will be a light goes to your eye, right? So that goes to your eye. And you can do a little bit extension over there. That should be coming off a light hit this guy and then goes in that direction. Okay, so should be something coming from here, hits this guy, and then hit your eye. At the bottom here, there will be a light hit your eye as well. And then that will be coming from one point of the building that hits this bottom edge of the mirror. Okay, so that hits that. So then it appears to you that you can back extend this ray that goes into your eye. Okay, and then also this guy back extend that. So then this is the portion of the building that will be seen by you, right? So looking for the edge. All right, now this is a geometry problem. So let's see, you have this guy 0.32, you have this 0.5, you have this 95.5, okay, and then 95.5 over here. Now let's take a look on this triangle here. So this guy here. This one in red here, okay? We are looking for this H, okay? And then this is 0.32, and this height of this small triangle here. Okay, so this small one and this bigger one. So we can see this small triangle And this big triangle, they are similar triangles, right? Because they share the same angles. So this is the same angle. This is parallel to that. So the small one and the big one, they are similar triangles. Okay, so for similar triangles, then you can have the relationship of the height of this small triangle over this side should be equal to height of the larger triangle over this height, right? So you can relate them there. So this one will be 0.5 meters for the height of this small triangle divided by the 0.32 for this side, okay? It should be equal to the height of this from here to here. Now we should take a look on the number carefully. So this is 95.5, and then we should include that 0.5 to be the height of the larger triangle. So 95.5 plus 0.5. So that would be 96 meters, okay? Would be the 95.5 plus 0.5. And over this h, that's what you are looking for, okay? So once you have set that up, then you can solve for h. All right, so in that case, h will be equal to, what you can do is multiply both sides by h, okay? Get rid of h on the right, so then h is on the left, okay? Then in that case, h would be equal to 96 divided by this, okay? Divided by 0.5 over 0.32, okay? So that would tell you this is going to be 61.44 meters, okay? So that's how large the part of the building can be seen. Okay. So up to this point, you can see this is pretty much geometry and trigonometry, okay? Still. All right. So if you guys are clear, we can move on. All right. Now, if you have several prime mirrors, you can put them together. So for example, if you have 3 of them, you can put them together perpendicular to each other. Okay, so in this case, so then if you have an incoming ray hits one of the mirror, it will get reflected several times and then comes back. Okay, so then this instant ray and then the final outgoing ray, they should be parallel to each other, but just in opposite direction. So if you have 3 mirrors, you can construct, this is called a corner refractor. Okay, so for that purpose. All right. Next, let's take the law of refraction, which you guys already studied last week for the lab in the lab. Now, to start get started, we'll first take a look the speed of light. Okay, so this was some experiment that was performed in the 19th centuries. Okay, so for people trying to figure out what's the speed of light. Okay, so one of the early measurement was performed by Michelson, used this method. So where there's a light source, this is a rotating mirror. Okay, it will hit. So there are mirrors here on each side of this rotating wheel. So light comes out of the light source, and then there's a fixed mirror. This is several kilometers away, and there's a detector to receive that light. Okay, so in order to see the light comes that is coming out from light source, you have to rotate this mirror at a certain frequency, so that the light comes through here will hit this and get reflect go back. Okay, otherwise if it's at different angle, then it will not be reaching the detector. Okay, so you can tune the frequency, you can monitor what's the time it takes, and then you know the distance the light will have to travel. So you can calculate that. Okay. So for these days, we have known that speed of light is a constant number that you can actually calculate from Maxwell's equations. It's equal to 1 divided by square root of epsilon naught times mu naught. This is the permittivity of vacuum. This is the permeability of the vacuum, okay? So it's 299,792,458 meters per second, okay? We usually just take 300 million meters per second for that, okay? And for the light to travel in 1 year, that's called a light year. That's a measure of distance. This is equal to 1 times the speed of light times how many seconds in a year, and then that gives you that number, 9.46 times 10 to the 15 meters. Okay, so that's how far the light can travel in a year. All right. Now, speed of light actually will travel will be different if it enters a media. Okay, so for the number we saw, it was the speed of light in vacuum. When the light enters a media, then the speed will be reduced by a factor called index of refraction. So that's equal to index of refraction equal to the speed of light in vacuum. So we usually use C for that purpose. And then any other speed of light in medium would be just the regular V for that. Okay, so if you do C divided by V, that gives you N. Okay, for index of refraction of vacuum, it's 1. You can do C divided by C, so that's 1. And then for any other medias, you can calculate. Okay. All right. So when light enters media, first you will hit the surface, and then as we know, if it hits the surface, it will be reflected. Okay, so if this is a transparent media, then part of the light will be reflected, part of it will be refracted that enters the media. Okay, so for the part that's above the surface, we have talked about that. So we'll just focus on the bottom part here when it enters the media. So this is governed by Snell's law that says n1 sine theta 1 is equal to n2 sine theta 2. So n would be the index of refraction of the media. Here in this case will be air times the incidence angle. All right, that should be equal to n2 index of refraction of this media, for example, glass, times sine of theta 2 would be this angle the reflected beam makes with the normal direction of the surface. Okay, so that's Snell's law. Now, if you replace the index of refraction with the definition of it, so n equal to c divided by v, then Snell's law can be rewritten as this guy, sine of theta 1 over v1, because n1 is c over v1, and then n2 is c over v2, so c will cancel out, so you only have sine theta 1 over v1 equal to sine theta 2 over v2 remaining. Okay, so that's another way of writing Snell's law relate to the speed of light in the medium. All right, so when you have this light enters a media, so if enters a media where its speed decreases, okay, so that means the index of refraction increase, because index of refraction is equal to speed of light in vacuum divided by speed of light in medium. So if speed decreases, that means index of refraction is increased. So if you look back here, so n1 sine theta 1 equal to n2 sine theta 2. So if n2 is greater in here in the media, that means the speed light will decrease. Okay, so then it will be bent. So this refract beam will be bent towards the normal direction. So this is the original instance beam direction in this direction. So it's bent towards that. Okay, and then on the other hand around, if you have the speed, the light comes from a media that has the speed of the light will increase. So that's the other way around. If you go from the glass enters the air, so then this is the original direction of this light will be bended away from the normal direction. Okay, so that's the first two sentences there. The third one says there's no change in direction of propagation if there's no change of index of refraction. Okay, so if the two median happen to be having the same index of refraction, then the light will not be bent. Okay, the direction of its propagation will stay the same. The last sentence here so says a ray of light goes from one medium to another along the normal direction. It's undeflected regardless of the index of refraction. Okay. So from Snell's law, you can see if instance angle is equal to 0, okay, so that means it's just coming in the normal direction, then theta 2 should be also 0, okay, so that's the fourth sentence. And this is should be the answer to your additional exercise in the previous lab, okay, so when it was asking why when the light hits the curved surface and then enter the air, it wasn't bent. So that's because the light actually is coming along the normal direction because you have a semicircle. Now the light is supposed to come in from the center of the curvature, hit the surface. So that's the normal direction for the instant beam there, okay? All right. And you guys probably noticed this if you put a pencil in the water or maybe more often that you put a straw in your drink, you'll see that it appears like the straw is being bended. Okay, so in that case, that's because the light comes from the straw or pencil, hits the surface and get refracted. Okay, so then it appears to be bended there. And if you notice that in like hot summer days, if you are driving on the road, you'll see when you look ahead on the road surface, there's image of the surrounding will appear, okay, on the road surface. That's because there's air density variation um, when the surface is hot. So then there's light air here, there's dense air on the top. So then there's actually index of refraction has gradient through different densities of the air. Okay, so then the light come from the surrounding object is not directly into your eye, but banded. So when it's banded, then it appears coming from the down here, which means the road surface. Okay. All right. We will take a look on a example on the Snell's law here. It says a submerged scuba diver looks up towards the calm surface of fresh water and notes that the sun appears to be 35 degrees from the vertical. The diver's friend is standing on the shore of the lake at one angle above the horizon. Horizon does the friend see the sun? Okay, so again, we have to sketch the problem and then see the geometry involved here. All right, so it says it's a calm surface, so it's flat. And I'm going to just draw one eye of the diver. So when he looks up, he sees somewhere 35 degrees. So that means sun ray hits his eye with vertical of 35 degrees. Okay. And then now it's probably coming at this angle, or actually the other way around here. Okay. You can imagine the sun in the sky there, and then one of the ray comes off the sun, hits the surface, and then hit the eye there. And there's a friend standing on the shore. So if this is the shore, and then he will look up the sun. So the sunlight, if you are looking at different rays, they are pretty much parallel to each other. Okay. So now it's asking for if this guy on the shore here look up, what will be the direction of the ray mixed with horizon. horizon here. So this is the angle you're looking for, theta angle. Okay, so that theta angle should be this theta angle. Okay, you're looking for this theta angle. So this is N1, and then this is N2, index of refraction for air. So you can look up for index of refraction for air, it's going to be 1.003. Okay. For fresh water, you can also look it up. It's 1.33. Okay. Those two, you can look them up. Now you know this angle, theta 2, this is the angle the refracted ray makes with the normal, and then you're looking for this angle, but you can calculate this angle theta 1 first, right? The instance angle, you can calculate first. Once you have that, this guy plus this guy will be the 90 degrees, so then you can calculate this, okay? After you figure out this theta 1. So you can apply Snell's law here. N1 sine theta 1 equals to N2 sine theta 2. Okay, you're looking for theta 1. So 1.0003 times sine of theta 1 equals to 1.33 times sine of the 35 degrees. Okay, so your sine theta 1 should be 1.33 times sine of 35 degrees over 1.0003. Now, a lot of times you can use just N1 index refraction for air to be 1. Okay, so because you can see decimal place will not affect the result. Okay, so if you are using 1.00, should be also fine. All right, so you can solve for your theta 1. Basically, you do sine inverse of this, sine inverse of what you have above. That will give you 49.7 degrees. Once you have that angle theta 1, then the angle theta can be calculated. It's 90 degrees minus that. So this will be 40.3. Okay. All right. Okay. So let's move on to the next section. So if we have a scenario that you have the light comes from a denser media, so that for this case, if light hits the surface here, and then you can see part of it will be reflected, part of it will enter the second media, so refracted. Okay, so theta 1 here, theta 2 there, and Snell's law will apply. N1 sine theta 1 equal to N2 sine theta 2. Now N1 is greater than N2 because this will be a dense material. This probably is, let's say this is just air. So in that case, you can see N1 is greater than N2. So then theta 1 has to be greater than theta 2 has to be greater than theta 1, right? Because N1 sine theta 1 is equal to N2 sine theta 2. If this is smaller, this will be larger. Sine is increasing function from 0 to 90 degree, okay? So you can see theta 2 is greater than theta 1. Now, if you increase theta 1, all right, then theta 2 will be increased as well. Now, at some point, theta 2 is going to reach 90 degree first. Okay, so when that happens, we call this as critical condition, because then if you keep increasing your theta 1, then you will have no more refracted ray enters the second media. It will only be fully reflected. Okay, so that means the light hit this one, will not enter the second media, but will be totally reflected. Okay, so when this happens, this is called total internal reflection. All right. You can calculate what's that critical angle by setting theta 2 equal to 90 degrees in Snell's law. So then sine of 90 will be 1. So Snell's law then simplify as n1 sine theta 1 equal to n2. And you can solve for theta 1 in that case given n1 and n2. So theta 1 will be equal to sine inverse of n2 over n1 here. Okay, where we call this angle to be the critical angle, theta c of this material. Okay, so that's in the case of n1 is greater than n2. Okay, the application of total internal reflection would be there's optical pieces in your binoculars, so that happens that when the ray comes in here, will not be refracted. Okay, it will be totally internal refracted. Okay, so in that case, the intensity comes in will be preserved 100% when it hits this. Okay, so these are where the total internal reflection happens. Okay. Also, the optical fibers. So the signal comes in, hits the wall of the fiber, and then will be totally internally reflected. Okay, so then you can keep 100% of the signal in the fiber. Okay, it's not entering the wall there. That means you don't lose intensity of signal there. Okay. All right. And that's on the total internal refraction. Let's move on to the next section on dispersion. Okay, so so this is how you see rainbow. Okay, or if it rained and then the sun just come out right after that, or if you can use prism to see that. So what happens is the white light, the sunlight is white light, is actually it's a mixture of different colors. All right, now different colors will have different index of refraction through a media. So those colors have very similar wavelengths. They are different by slight amount, and their wavelengths are, or their frequencies are very similar to each other. However, index of refraction is proportional to the wavelengths of the light. Okay, so for less small differences, it actually matters when the white light hit the prism here, then they will be refracted at different angles, slightly different angles. Okay, so if it hits this prism wall once and then the second time, then it will be further separated. So then you'll see different colors coming out of the prism on the other side. Okay, so this is called dispersion of light. And this is how you see the rainbows. Okay, so when you see the rainbow, that's because the white light coming from the sun hit raindrops in the air, then get refracted. So then the lights will be separate out slightly one time when it hits this guy. Now get reflected and then hit the exit the raindrops a second time here, get reflected more. Okay, so you can calculate according to the index of refraction of different light. You can see violet will be at about 40 degrees if you look it up from the horizon, and then red light will be about 42 degrees. Okay. And sometimes if you are lucky, you may see double rainbows. So there's a primary rainbow, there's a secondary rainbow. Okay. That's because so those two rainbows, they are formed slightly different. For the primary, as this guy hits the air water drop, here get reflected with just one time inside the air, the water droplet. For the secondary, it gets reflected twice inside the water droplet. Okay, so the secondary is dimmer because it's reflected twice, so it loses intensity more. Okay, the secondary rainbow will be appear at above like 51 degrees. Okay, so that's above this primary rainbow. Okay, all right. Also, you'll see like this halo around the sun sometimes. So this is the it's because there's hexagonal ice crystals in the air. Okay, so in the air there's when the temperature is cold, there's ice crystal there, and then the sunlight will be deflected in that case. Okay, sometimes you see these two bright ones, they are called sun dogs. Okay, that's again because the ice crystals in the air. All right. So let's take a look on one example on the dispersion of lights. So this one says, let's see. So it says the index of refraction for red light in a certain liquid is 1.305, and the index of refraction for violet light in the same liquid is 1.336. Okay, so violet light is having larger frequency than red light, so this is it's having a little bit more index of refraction here. It's asking you find the dispersion for red light and violet light when both are incident from the air onto the flat surface of liquid at 45 degrees. Okay, so this is what's happening. When they come in the same angle, hit the liquid, because their index of refraction is different, so they are going to be enter the liquid at different angles. And you're looking for that difference. So let's say this is the air, and then this is the liquid. Okay, so for index of refraction of air, we are going to say that's N1. So that's just use 1 this time. And then for index of refraction in liquid, N2. Now you have red light, so let's say N2R, that's a number, it's 1.305. For index of refraction in the liquid, N2 for the violet, that's 1.336, okay? Index of refraction for different colors in vacuum, they are the same, that's equal to 1, okay? And then for index of refractions for the different colors in air, they should be also about the same 1. So because it's 1.0003, that's pretty much 1. So you can treat them as the same. So for red light and then for violet as well, okay? So that's the same one. Now let's see, this is the normal line when the two comes in at the same 45 degrees. So let's say here, and then I can use another color here to just kind of indicate that they are coming at the same angle, okay? So for one of them will be reflected. This is for the red light. Oh, I should use the red, maybe that would be better. And for violet, it's going to be reflected at a different angle. Okay. So you're looking for this angle, this is theta R. And then this angle, this is theta V. You're looking for theta v minus theta r. So that means you need to know theta r and theta v. Okay. So we can apply Snell's law for the violet light. That will be n1 sine theta 1 equal to n2 v sine theta v. And this theta 1 is given 45 degrees. Okay, so 45 degrees. N1, you can just use 1 times sine of 45 degrees equals to N2V will be 1.336 sine of theta V. Okay. So you can divide both sides by 1.336 to get rid of that. Okay. So then sine theta V is equal to that. Sine of 45 over 1.336. Okay. You can then do sine inverse of this equal to sine inverse of the other side. Okay. To solve for your theta v, so theta v then is equal to sine inverse of that. That will be equal to 31.956 degrees. Okay. So when you're solving for two angles that are close to each other, make sure you keep extra digits, okay, to avoid some potential rounding error. So I'm keeping 5 digits here. For the red light, you can apply Snell's law again. So n1 sine theta 1 will be equal to n2 r sine theta r, the red light, okay? So this is similar 1.00 sine of 45 degrees equal to n2 r, it's 1.305 sine of theta r. You'll be dividing both sides by 1.305, okay? And then sine of theta r will be equal to sine of 45 degrees divided by 1.305. In that case, take inverse, sine inverse of the both side equation, sine inverse to solve for your theta r, okay? Your theta r will be equal to 32.809 degrees. All right. Then you can calculate the difference of the two. So theta v over theta r, 31.956 minus 32.809. That gives you minus 0.853 degrees. Okay, less than 1 degree. Okay, of the difference. And I think there's a problem in the assignment that you are calculating the dispersion of the two lights through a prism here. So I don't remember what's the instance angle. Okay, but then you apply Snell's law to the two lights on this surface one time. So then one light gets reflected there and there. Okay. And then, so this is Snell's law one time, you'll figure out what's the angles here. And then Snell's law a second time when it hits the wall the second time, okay? And then you'll figure out the angles there too, then calculate the difference, okay? So just repeating what we did one more time for that, for the second surface on that one. All right, so any questions you guys might have on this one? Let's see. So if not, I think we'll stop here for today, okay?